Right now, 26,000 light-years away, something with the mass of 4 million suns is sitting in total darkness at the exact center of our galaxy, and every star in the night sky, including our own, is quietly falling around it. It is Sagittarius A, the black hole at the heart of the Milky Way. The full story. Chapter 1. Hidden in plain sight. Point an ordinary telescope at the constellation Sagittarius on a clear night and you still will not see it. Between Earth and the true center of our galaxy lie roughly 26,000 light-years of interstellar gas and dust, and that dust is thick enough to dim visible light by a factor of trillions. For nearly all of human history, the actual heart of the Milky Way, the densest and most violent real estate in the entire galaxy, was simply an invisible blank patch of sky, hiding behind a curtain no eye or optical telescope could ever pierce. The first crack in that curtain came almost by accident. In April 1933, a young radio engineer named Karl Jansky, working for Bell Telephone Laboratories, had been assigned a mundane job: find out what was causing static on transatlantic radio calls. He built a rotating antenna, nicknamed the merry-go-round, to hunt down the source. Alongside thunderstorm static, Jansky kept picking up a strange steady hiss that rose and fell with the stars rather than the sun, and traced it to the direction of the constellation Sagittarius. Jansky had, without fully realizing it, founded an entirely new branch of astronomy and pointed it straight at the galaxy's best-kept secret. Radio waves, unlike visible light, passed almost freely through the dust clouds that block our view, which meant scientists finally had a way to look past the curtain. For decades afterward, though, the source he had stumbled onto stayed nothing more than a fuzzy blur of radio noise, his true nature completely unknown. Nobody yet suspected that, buried inside that blur, was something almost too extreme to believe. It helps to understand just how big a haystack that hidden center actually is. The Milky Way spans roughly 100,000 light-years and holds somewhere between 100 billion and 400 billion stars, our own sun among them out on a comparatively quiet spiral arm. By the late 20th century, astronomers had also begun noticing something curious in other galaxies. Many of them seemed to have an extraordinarily massive compact object buried at their centers too. If the Milky Way followed the same pattern, whatever Jansky's static was hiding would not just be a curiosity. It would be the galaxy's gravitational anchor. Chapter 2. The object that shouldn't exist. It took 4 more decades of steadily improving instruments before anyone could see past Jansky's blur. In February 1974, astronomers Bruce Bellick and Robert Brown used a technique called interferometry, electronically linking separate radio dishes together so their combined resolving power far exceeded any single telescope's. Sifting through the noisy radio glow at the galactic center, they isolated something new, an extremely compact source, far smaller and far more concentrated than the surrounding gas cloud it sat inside. Whatever this object was, it was tiny, and it was intensely bright. Robert Brown gave the source its lasting name in a 1982 paper, calling it Sagittarius A star. The asterisk was borrowed from the notation physicists use for an atom in an excited energy state, because, as Brown later explained, the object was simply exciting. It was an oddly playful, almost inside joke of a name for what astronomers were increasingly convinced they had found not just a bright radio point, but the telltale signature of a supermassive black hole, sitting at the exact gravitational center of the entire Milky Way. A name and a radio signature were not proved, though. Detecting bright radio emission from a compact region does not by itself demonstrate that the black hole is responsible. Other exotic objects could theoretically produce something similar. Skeptical astronomers wanted direct, unambiguous evidence, something whose gravity could actually be measured, not merely inferred from static on a receiver. That evidence would end up coming from an unlikely direction, entirely not from Sagittarius A itself, but from the ordinary visible stars swarming in tight orbits around it, close enough to feel its pull directly. In the meantime, rival explanations stayed on the table. Some astronomers argued the mass at the galactic center might simply be an extremely dense cluster of ordinary stars and stellar remnants packed unusually close together, but not exotic at all. Others pointed to a nearby, separate structure called Sagittarius A East, the shattered remains of a supernova, and wondered whether the two radio features were being wrongly linked together as one object. Sorting out which explanation was correct meant astronomers needed something no radio telescope of the era could provide: a direct moving measurement of gravity itself, not just a bright dot on a receiver. Chapter 3: Racing the Stars. Starting in the early 1990s, two rival research groups, one led by Reinhard Gunzel in Germany, the other by André Ghez in the United States, independently began the same painstaking project, pointing the largest telescopes on Earth at the same tiny patch of sky, year after year, and tracking individual stars as they moved, using a technique called adaptive optics, which corrects in real time for the blurring caused by Earth's own atmosphere. Both teams sharpened their images enough to watch those stars trace out full orbits, like distant planets circling an invisible, unseen sun. One star became the project's centerpiece. Say, astronomers simply call it S2. It loops around the galactic center on a tight, elongated orbit, lasting roughly 16 years, and in May 2018, it swept to within about 120 times the Earth, sun the distance of whatever invisible mass it was circling, accelerating to nearly 2.5% of the speed of light, more than 7,000 kilometers every single second, before slingshotting back out into the darkness. Later observations found other stars diving even closer still, one passing within roughly 12 times that same distance. By timing orbits like S2's with extraordinary precision over nearly 3 decades, both teams independently calculated the mass required to whip a star around that fast on that tight a path, roughly 4 million times the mass of our Sun, all packed into a region no larger than our own solar system. No ordinary cluster of stars could hide that much mass in that little space without its members constantly colliding. The only object general relativity allowed was a black hole. In 2020, Gwenzel and Ghez shared the Nobel Prize in Physics for turning that inference into certainty. None of this was easy observing. The stars near the galactic center appear as impossibly faint, closely packed pinpricks of light smeared further by Earth's turbulent atmosphere. So both teams relied on laser guides, stars' artificial points of light beamed into the upper atmosphere, to help their adaptive optic systems. Genzel's team worked from the Very Large Telescope in Chile, Gez's from the Keck Observatory in Hawaii, and for years the two groups pushed each other to greater precision. Stu's orbit even let them test something extra: Einstein's general relativity, confirming a subtle reddening of the star's light exactly as predicted, near such extreme gravity. Before we move on to the next chapter, if you're enjoying this, please like the video, follow so you don't miss future videos, and turn on notifications. Chapter 4: A Portrait of the Beast. Knowing a black hole's mass with certainty is still not the same as actually seeing it. In April 2017, more than 300 scientists across dozens of institutions linked 8 radio observatories scattered from Hawaii to the South Pole to Chile, synchronizing them with atomic clocks so precise that the entire planet effectively became one single virtual telescope. This project, named the Event Horizon Telescope, aimed itself at 2 targets simultaneously: the enormous black hole at the center of the distant galaxy, M87, and our own, far smaller, much closer, Sagittarius A asterisk. Imaging Sagittarius A turned out to be by far the harder of the 2 problems, precisely because it is smaller. Hot gas swirling near its event horizon completes a full orbit in only about 30 minutes, compared to roughly a month for the much larger black hole in M87. That meant the picture itself kept shifting while the telescope was still gathering light for it, like trying to photograph a hummingbird's wings with a camera that needs hours just to open its shutter. Untangling that blur into a coherent image took the collaboration 5 additional years of computation. On May 12, 2022, the team finally unveiled the result: a glowing, slightly lopsided ring of light wrapped around a perfectly dark shadow. The silhouette, Sagittarius A*, casts against the superheated gas swirling just outside it. The ring measured roughly 52 million kilometers across, smaller than the distance from the Sun to Mercury at its closest, yet somehow containing 4 million solar masses. It was only the second confirmed image of a black hole's shadow ever captured, and the first direct portrait of the object anchoring humanity's own home galaxy. The engineering behind that picture was almost as remarkable as the picture itself. Each of the 8 observatories needed clear sky simultaneously, on the same handful of nights, an alignment that is far from guaranteed, across sites as far apart as Antarctica, Hawaii, Chile, and Spain. Every dish recorded a flood of data so enormous it could not be sent over the internet. Instead, hundreds of hard drives were physically packed into cases and flown by airplane to central processing centers, dated by atomic clocks, accurate enough to synchronize signals of a billionth of a second. Chapter 5. The Sleeping Giant Wakes. For a supermassive black hole, Sagittarius A is strangely almost disappointingly quiet. It barely feeds, pulling in only a faint trickle of gas compared to the ravenous, blazingly bright black holes lighting up the centers of many other galaxies across the universe. But quiet does not mean motionless. In 2011, astronomers spotted a small compact cloud of gas, nicknamed G2, falling on what looked like a direct collision course toward the black hole, and much of the astronomical community braced for a dramatic, once-in-a-generation fireworks show as the two collided. When G2 made its closest pass in 2014, astronomers watched with every instrument available, waiting for a dramatic outburst of radiation. Instead, the cloud stretched under the tidal forces, survived and slid past, largely intact, suggesting it was denser than first assumed, possibly a diffuse cloud wrapped around a hidden. Sagittarius A itself barely reacted at all. Then, seemingly out of nowhere, in January 2015, it produced the single brightest flare ever recorded from the black hole, blazing roughly 400 times brighter than its already faint, everyday glow, with no clear trigger identified. More recent evidence suggests this quiet giant has not always been so calm. Using NASA's XP telescope, astronomers traced faint X-ray light echoing off distant gas clouds near the galactic center, essentially reading a delayed light-based fossil record, and concluded that Sagittarius A flared dramatically, roughly 200 years ago. It increasingly looks less like a permanently sleepy monster and more like one that wakes, feeds briefly, and dozes off again. On a Riven, astronomers are only just beginning to reconstruct. Compare Sagittarius A to a quasar, the blazing hyperactive black hole seen at the centers of some distant young galaxies, and the contrast is stark. Those objects can outshine every star in their galaxy combined, gorging on enormous inflowing disks of gas fast enough to blast out radiation across the visible universe. Sagittarius A does none of that. It sips instead of gulping, and astronomers now think that difference may say less about the black hole itself and more about the Milky Way's own quiet, comparatively uneventful history of galactic mergers and gas supply over billions of years. Chapter 6. Spin Shuttle and what comes next. One of the strangest open questions left is exactly how fast Sagittarius A is spinning on its axis. A black hole spin warps the space immediately surrounding it, flattening its event horizon somewhat the way a spinning ball of dough flattens outward under its own momentum, and that spin can dramatically affect how nearby matter behaves. Different research teams, using different methods and different slices of the same data, have published estimates ranging anywhere from roughly 60 to over 90% of the theoretical maximum possible spin. The exact figure remains genuinely disputed, and nailing it down precisely is one of the field's most active current goals. The Event Horizon Telescope collaboration is far from finished. Newer observing campaigns, additional radio dishes joining the global network, and space-based instruments like the James Webb Space Telescope have already caught Sagittarius A, producing rapid, unpredictable bursts of light within minutes of each other. The long-term goal is to turn that single static 2022 snapshot into an actual movie, frame by frame, footage of gas churning and flaring around the event horizon in close to real time. Every additional dish added to the array sharpens the resolution a little further, inching astronomers closer to that goal. Beyond satisfying curiosity, Sagittarius A matters because it is the closest laboratory in the universe for testing gravity at its absolute most extreme. Every prediction general relativity makes about warped space, bent starlight, and slow time can be checked here with a precision impossible anywhere else, simply because nothing else this massive and this dense sits so relatively close to Earth. Proposed next generation arrays expanding the Event Horizon Telescope with more dishes across more continents aim to sharpen that laboratory even further, turning a single historic photograph into an ongoing, evolving. Sagittarius A will never engulf us. Earth orbits far too safely, tens of thousands of light years out on a quiet spiral arm, for that to ever be a real danger. But every star you can see on a clear night, our own sun included, is slowly circling that dark, silent point at the center, completing one full loop of the galaxy roughly every 230 million years. We do not just happen to live somewhere near a black hole. We live quite literally in permanent orbit around one. Space keeps its best secrets in plain sight. Follow cosmic blind spot and start seeing what everyone else misses.